Welcome to our talk. This is Riccardo Poli and Bill Langdon. You can hear him probably. So here is the title of our talk. It's a Markov chain model of machine code program execution and halting. So let's start with a motivating slide. Okay, there we go. So we know that we all know the halting problem. It's the problem by which, if I give you a program, it's impossible to decide whether the program is going to halt or not for all possible input situations. And this problem was proven to be undecidable. That is, it's a problem where logic and theorem proving cannot do any good by Alan Turing. And so it's a problem where we don't know the answer and we can't actually discover it. But in this talk, what we want to say is that actually for certain types of programs and CPUs, it is possible to give an answer, and in fact it's a probabilistic answer. And with probability 1, all programs without a halt instruction are not going to terminate.
Right, thank you, Riccardo. We'll start with an overview. So the idea is we have some results in Foundations of GP which look at linear GP systems, and we want to see if we can extend those to Turing-complete GP. In particular, we add memory and loops to a GP system and see what impact that has on the fitness landscape. We're going to define a very small, in some ways the minimal Turing-complete machine. I'm going to run some experiments on that machine trying to map out the fitness landscape. Riccardo will then come back and talk about the Markov chain model which explains those results, and then we'll conclude with the implications of this work. So, as I've said before, we have these results that as programs get bigger, their functionality tends to a limit. And what we want to do is see if that's true also for Turing-complete programs. And in fact, we've given away the answer already. We know that there is a limit, and in the limit, the fraction of halting programs goes to 0. Now, the minimal Turing-complete machine we've called the T7 simply because it has 7 instructions. The first of those is add. From add, we can construct all the other operations, the Boolean logic. We can construct subtraction simply by adding the complement. We can construct multiply by repeated addition. Assuming we have subroutines and so on, we can then build all the remaining complex operations from just that single primitive. We also need a conditional statement, which you'll see later is called a branch if overflow set. So you'll see various BVS instructions, and we have operations to move data around memory. We have operations to save and restore the program counter, so we can construct gotos, we can construct subroutines, and finally the program stops when we reach the end of the reach its end. On slide 6 we have a picture of the T7 architecture. So on the left hand side we have the CPU. In green there it's executing the AND instruction, and a rank of memory registers. So in the example there, the add instruction is reading a byte from register 72, another one from register 27, adds those together, produces a 9-bit answer. 1 bit goes into the overflow flag, so AND is the only operation that actually sets the overflow bit, and the other 8 bits are written back into register 45. The experiments we're going to run are simply to sample at random from the search space. So we'll build up a picture of the whole search space by sampling at various lengths. So we'll sample at lengths between 30 and 16 million. And we're going to generate at least 1,000 random programs of each length. We run them from a random starting point with a random input, and the first thing of interest is to see how many of those programs actually stop. So that's plotted on the next slide, and the two lines, the first line is at the top there in red is the fraction of programs which do not terminate, so they just run forever or until we get bored. And you can see that starts off at about 60% and grows almost to 100% as programs get bigger. The blue line shows that the fraction of programs which never loop, and you can see that starts off in a region of about 30% and falls away towards 0. Okay, so we've seen the experimental results. We're now going to look at modeling these random programs. The first model which I'll present is based on the idea that we have repeated before we get to the point where the program starts looping. We have a sequence of random instructions, and the contents of memory are random, and those two are uncorrelated with each other. Given that, then 1 in 7 instructions is just going to be a jump to a random location, and in addition we also have the conditional instructions. Now the T7 architecture has been set up so that it's as unbiased as possible, and in particular the chance of the overflow flag being set is 50%. So in addition to the 1 in 7 instructions which jump, we also have another half instruction which also causes the program counter to move to a random location. So in total we have 1.5 out of 7 instructions which cause us to jump. In other words, there are approximately 4.6 program instructions in sequence, and then we come to a jump. Now on the next slide we have a little model which shows we have this as a group of sequential instructions followed by a jump. Now the point being, we can enter that group of sequential instructions at any point, and we will filter through until we come to the jump, and that jump will take us to a random location. So if we enter the sequential code at any point, we're guaranteed to pass through at least the end instruction. And the model that we're going to set up is what I've called the segments model, and what this does is to divide the whole program into L over 4.67 segments of equal length. The last instruction of each segment is going to be a jump to a random location, and what we want to do is look at how programs can form loops, and the way they form loops is by jumping to a segment which they've already executed. The other thing that's of interest is if we jump to the last segment in a program, then we must filter through to the last instruction in that segment, so we'll come to the end of the program. So what I'm looking at here now is, supposing we've run I segments so far, the chance of forming a loop is simply the I times the number, I divided by the number of segments. The chance of halting is simply 1 in n, and of course the difference between those is the chance of something essentially of continuing. So that, and now the chance of halting immediately after segment I is the chance of 1 in n, as before, times the chance that we haven't already halted, or the chance that we haven't already got stuck into a loop, which is there in green. Now a bit of algebra, we can rearrange those terms to give the total halting probability. So we sum over all values that I can take, and that gives us something which is very close to the square root of pi over 2n, where n is the number of segments. So the point being, the probability of a random program halting falls as the square root of the length of the program. Here we've plotted in red the segments model, so that's the straight line, and you can see that it follows the trend of the blue line, which is the experiments, reasonably closely. In addition to that, the also plotted there is the Markov model, which is highlighted in red with the square boxes, and you can see that has the same trend, but it follows the data slightly better. So in other words, the segment model is correctly predicting this 1 over square root rule, which is what the data shows, the experiments show. The next slide shows, perhaps we shouldn't be too downcast about this, because although the number of programs that halt as a fraction is going towards 0, of course the number of programs in total is increasing exponentially fast. And what I've plotted here is the total number of halting programs versus their length. And you can see there that rises exponentially, and in particular, if we take the largest programs we're worried about, so 16 million odd, then the number of halting programs is 10 to the 100 million, which is a truly ridiculous number. The last thing that we want to look at with the segment model is we can also use it to predict how long the halting programs will run for. In other words, the expected runtime. And on slide 17 we've plotted the experimental results, which show that the experimental results in blue there, which show that as before, the segments model predicts the general trend of the data, particularly for the shorter programs, but as the programs get over, say, 100,000 or so, the experimental data starts to move away from the predictions. And we believe that's an artifact of the small memory size used in this machine. So there's only 12 bytes of memory on this machine, and believe that is causing the memory to become correlated with the programs as they execute, meaning it becomes easier to form loops, and so the simple segments model starts to break down. Notice again that the Markov model with the red with the squares on is slightly more accurate, but shows the same general trend. And now Riccardo will give you the Markov chain model.
So okay, so the Markov chain model. Well, obviously, if we want to do a Markov chain, we need to talk about states and then transitions between states. There are so many states in a computer executing programs. So even with 96 bits of memory, which is not much, but there are 2 to the 96 possible states in there. So it's impossible to actually run a chain of that size, because it would be a 2 to the 96 times 2 to the 96 size matrix. So what we have done is to actually try to concentrate on states that are really important for us and states that are perhaps not as important. So we start from state 0, which represents the fact that we have executed no instructions, and in general states for us will represent the number of instructions executed. So state 1 means we have executed 1 instruction, state 2 we have executed 2 instructions, and so on. Now, as you can see here, however, it's state I is in general we have executed I instructions, but we have not executed any loops. So as soon as we execute a loop in a sequence of instructions, we'll say that we reach the sink state. Now we call it the sink because it's sort of a big garbage bin which collects all of those states of the machine where there is a possibility that we will not halt, and we will therefore take a very conservative view of what the sink should be. That is, as soon as a program loops, we will assume it's not going to halt. So our chain will provide essentially some lower bound about the probability of halting. There could be programs that halt in the sink, but we will assume that there aren't. So in addition to these states, we also have a hold state, of course, which is the situation where we reach the last instruction in a program, and that instruction is not a jump, or if it's a jump, it's a conditional jump, and it doesn't get executed. So we go beyond the end of that program. Okay, so we described the states. We need to talk about, naturally, the transition probabilities between states in order to get a complete model. Now, in this slide, we've got a diagram that is going to help us understand how we compute these transition probabilities. So obviously the main transition probabilities are those that tell us how we go from a particular state I, that is, we have executed I instructions, to another state. But from state I, there can only be very few outcomes or successor states. That is, if we have executed I instructions, all we can do is execute one extra instruction, so we can reach state I plus 1, like it is indicated here, or we can halt, perhaps, like here, for example, or we can get to the sink. That is, we find a jump instruction that leads us to some re-executed code, and this is, for example, the situation in that particular node there. But obviously there are different ways of getting to one of these states, and these are represented in this state diagram. So we have executed I instruction, so we are at this particular node, and we need to ask the question, is the current instruction the last in the program or not? Because if it is the last in the program, then we are in this situation, and then we have a chance of halting now, but only if that instruction does not cause a jump. So I'm talking about causing a jump rather than being a jump, because as we said before, the branch instructions will jump only in 50% of the cases for random programs. So if we did jump, then there is still a chance that we don't loop if we land on an instruction that is new, and this is the situation depicted there. But of course, if we did land on an instruction that wasn't new, we will get to the sink instead. And this diagram has got all these possible situations depicted. So there are three ways of getting to the next instruction I, without looping. There is one way of halting, and there are three ways of reaching the sink. One I have highlighted before, and the other two are here. That situation. So you've seen that in the main tree that I've shown before, we had several probabilities labeling the nodes in the tree, and what we need to do in order to construct a Markov chain is really to work out what those numbers are. They were called P1, P2, P3, and P4, and what we need to do now is to look at how we can estimate those numbers to get a complete model, a complete Markov chain. So if we start from P1, P1 is the probability that a particular instruction you're executing right now is the last instruction. Now, obviously, as we said before, we start from the execution of a program from a random position. We know that initially the memory is randomly randomized, and so we know that any jumps in the early stages of execution are going to random locations. We're going to make the assumption that that will continue even later during the execution of programs. We'll still keep jumping at random positions. So it's kind of easy to see that the probability of an instruction being the last is essentially independent on how many instructions have been executed before, because what we're talking about here is that there is one last instruction in a program out of L possible instructions for a program length L. So the probability that during the execution we meet that final instruction is 1 over L. So the other important probability that we need to calculate or estimate is the probability of an instruction causing a jump. Now, we know that there are two types of instructions in a language, and in particular in T7. There are unconditional jumps, there, and conditional jumps, there. This flag bit here, I'm sorry about the typo, is the flag bit. Is set with a particular probability that in T7 we estimated to be 50%, but it could be any other particular number depending on the instruction set. So because we want the model to be generic, we haven't used the data for T7 in this particular calculation, but the generic formula is indicated here. So in order to calculate the probability that the current instruction will cause a jump, all we have to do is add the probability of unconditional jumps to the probability of conditional jumps and the flag being set. Now, of course, for T7, you can see the calculation at the bottom of the slide. We get that the probability 3 over 14 of the current instruction causing a jump. Okay, so the next probability that we want to compute is the probability of finding a new instruction after a jump. This is very important because if we find a new instruction, then we can continue the execution, we don't get to the sink. So we know that the program counter after a jump is going to be a random number, so it's going to be between 1 and L. But obviously in state I, we will have executed already I instructions, and so the number of available slots, if you're jumping at a random instruction and you want to find a new one, is only L minus 1. For that reason, the probability of finding a new instruction after a jump is L minus I over L, where again L is the length of the program. So the last calculation that we need to do is calculate P4. So obviously the more jumps we have executed, the more fragmented the map of these instructions will be. So in terms of the blocks that of code that Bill was talking about earlier, then we would find lots and lots of blocks sprinkled about in the map of the instructions. The more fragmentation there is, the more it's likely that we're going to find an old instruction as we execute the program sequentially. So we should expect to see that indeed the probability P4 is going to decrease as the number of jumps grows. So what we need to do to estimate this probability is to calculate the expected number of fragments that we have executed by the time we reach instruction I. And this number is provided down here. This is the number of expected jumps, is clearly simply given by the probability of jumping times the number of instructions that we have executed, this number I, so far. Simply because this is every time you decide whether you're going to jump or not, it's a Bernoulli trial with probability P2, success probability P2, so the number of jumps is going to be binomially distributed. Okay, so once we know the expected number of jumps, it becomes possible to calculate the probability of a previous executed instruction, that a previously executed instruction is found after a non-jump. And it is simply given by the ratio between the number of jumps and the number of instructions remaining to be executed or unexecuted after, given that we are in state I, and therefore we have already executed I instructions. So the number of remaining instructions is L minus I minus 1, and the number of jumps is J, so the ratio between these two gives us the probability of finding a previously executed instruction after a non-jump. The complement from 1 of that gives us P4. And now obviously we don't know J, which is a stochastic variable really, it's binomially distributed, but we know the expected value of J, so what we've done here is to actually use in the equation the expected value that we calculated before to compute an estimation for P4. When we tested this model with this particular estimation, we noticed that there were deviations from the experimental data. So a much more precise model considers the probability that blocks can be contiguous. That is, the number of jumps is an estimator of the number of contiguous blocks of instructions executed, but it's always possible that blocks executed during before different jumps actually end up being contiguous. So really the probability of finding new instructions will depend, after a non-jump, will depend on the number of blocks, not the actual jumps. So in this more refined model, we estimate the expected number of blocks, which is indicated here, and as you can see, the calculation makes use of the estimated number of jumps, but then it needs to correct that by a second term that considers the probability of blocks being the blocks generated by every single jump actually being contiguous. And with that new calculation, we are able to compute a much more precise P4. So since we've now calculated all of the transition all of the probabilities in the event diagram showed at the beginning, we are now able to compute the probabilities of reaching any particular type of leaf. So if, for example, we are interested in the probability of looping, that is the probability of from state I reaching a sink, then that probability is given by summing all of the paths in the diagram that is shown below. Now these paths are the one in green here, the one in yellow there, and the one in red there. And when I talk about paths, what we need to do along a path is to multiply the probabilities that are encountered along that path. So like in this particular case, if we want to calculate the probability of the sink being reached, we need to multiply P1 by P4 and by 1 minus P3. And similarly, we do the calculations for the other paths, and then we simply add those products together. When we've done these calculations, we find that we have computed the probability to go from the sink state, so this symbol here is actually a P, and likewise for the symbol down there. So what we've just done is added the three contributions, the three paths. One is this one is this one, and the remaining one is this one. So we have effectively, by adding the paths together, we have calculated the probability to go from having executed I instructions to looping. If we repeat the same operation for the other states of interest, for example, if we're interested in the probability of going from state I to the whole state, or the probability of going from the state I to the state I plus 1, then these are again sums over products calculated along the paths. There are really no other probabilities that need to be computed in order to proceed to the calculation of the Markov matrix, the transition matrix for the Markov chain, which is shown as an example in this slide, where I computed the matrix for the T7 computer, and for the case where L was a very small number, 7. So that gives us a matrix that is 9 by 9, because we need to extend, obviously, as I said before, we've got states 0 to L minus 1, and these are represented here as rows, and here as the corresponding columns. But also we've got the loop state, or sink as I called it before, and the hold state. So this matrix represents the probability of going from every state to every other state. And as you can see, the matrix has got some interesting structures, and this is one of the reasons actually that we can then go and do calculations very, very efficiently with this matrix. Once we've got the matrix, we can compute the future very, very easily. And this slide shows the calculation. All we have to do in order to compute the distribution of states for the chain in the future is to multiply, or to take power, appropriate power of the matrix, and that will give us the probability of going from any particular initial state distribution to the state distribution after I instructions. So if we want to know what happens after I instructions, take m to the power of I and multiply that by the probability distribution you start with. Now, because we know that every program will start from state 0, then the probability distribution over states is just a vector with 1 for state 0 and 0 otherwise. For example, for the chain I've just described, suppose that we iterate the chain for 3 instructions. Clearly, there are only 3 possibilities there. Either we go to the next state, which is we execute 4 instructions, and that is given with the probability 64% approx. We loop with the probability around 16%, or we halt at the next instruction with a probability 20%. But naturally, the distribution that we are most interested in is what happens if we iterate the chain up to its extreme limit, which is when we execute L instructions, as indicated here. So if we execute L instructions, we can calculate the probability of programs halting. It's simply the last element of the resulting state vector. If we have to compute powers of a large matrix, then one might be worried about the efficiency of this calculation. And it shows in this slide, certainly the calculation is potentially exponential. What's nice about this model is that there are lots of zeros in the Markov matrix, and in fact it's possible to reorganize the calculation in a very efficient way. So we can calculate both the halting probabilities and, very interestingly, the expected number of instructions executed by programs that are going to halt before they halt for very, very large programs. And we can do that essentially in a couple of minutes with the C implementation of our code. The slide shows that the squares, the dark dots there, they represent the experimental data for programs that go from around a few instructions to several million instructions, in fact 16 million. And there you can also see the Markov chain estimate, which is shown by this line here, and you can see how close the fit is. Now, this can't be just by chance. I mean, we are talking about a very good fit over 6 or 7 orders of magnitude in program sizes. So clearly there is something very good about the model. Now, when you then use these halting probabilities to do other calculations, then errors may accumulate a little bit more. But still, like in the case, for example, of the expected number of instructions executed by programs that halt, as you can see, I mean, again, the squares are the experimental data, and you can see the saturation that Bill was talking about due to the memory becoming non-random for very, very long programs. But you can see that the fit between the Markov model, which is this line here, and the actual data is very good for perhaps 4 or 5 orders of magnitude. And in fact, we've also modified the model so that it can account for the memory saturation, and you'll find more details in the paper, but essentially we are able now to calculate much more precisely the expected number of instructions executed by a program. So the chain is very, very accurate also when you use it to calculate the derived quantities for something like 7 or 8 orders of magnitude. We can now combine these new results on the halting probability with the previous results on the limited distribution of functionality. Now what is different here is that when we consider programs that can have loops, then what matters is really how many instructions get executed before the program reaches the halt state. And this number is not the same number as the number of instructions in the program. For that reason, it's very important to have this estimate on the expected of the number of instructions executed by halting programs. What applications are there for this characterization in the world of GP? Well, of course, we want to be able to do GP with Turing-complete CPUs, but obviously we may have problems because only a fraction of the programs that we execute will hold, and so in many cases the programs that don't hold are considered to be useless, and we tend to give these programs a zero fitness. So only a fraction of our population is really used in terms of evolution, and that's determined by p-halt. So we do have an effective population size that may be much smaller than the actual population size, and if it's too small, then there will be virtually no evolution going on in the system. So clearly this is not possible. We need to correct that, but how do we correct it? Well, there are many ways of doing it, but certainly one is to try and control the halting probabilities, try to act on it, modify it, improve it. This graph, you can see that over here we've got the halting probability for programs, and here we have the probability of using jump instructions in the search. And so clearly the fewer jump instructions we use, the higher the probability of halting these programs. And so all of these curves up, tend to increase as we go to that region and decrease in the other region. So one way of controlling p-halt is certainly to reduce the probability of using jump instructions when we initialize the population, and allow evolution to decide whether to use more of those if necessary. The other thing that we can do is, of course, to change the length of the programs that we search. For example, for very short programs we have a much higher halting probability than for very long programs. So another consequence is that, well, we've got all of these non-halting programs. What should we do about them? Well, what we can do is to try to set a time limit beyond which we are really confident that the program will not terminate, and so we can abort that program. But how should we set this time limit? Well, the theory, the Markov chain, can tell us, because we can calculate the expected number of instructions that a halting program would execute, and multiply that by some relatively large number, like 10, for example. Then this new limit would give us a probability of 99.999% that all programs that would hold within this time limit. So if we kill a program after this time, we know that we are making a mistake only in 0.0001% of the case. And of course we can also calculate through the Markov chain and this expected number of instructions and the whole probability, we can calculate the expected runtime, at least at the beginning of the run, for a GP system. So what we have done in this work, we have found empirical results and a simplified model of program execution based on the segments that predicts that the halting probability scales like the square root of the length of the programs, or better, 1 over the square root of the length of the programs being executed. We have also found a Markov chain that describes the execution of programs, and of course also the halting of programs, which is very accurate. And also it's practical, because we can really execute this chain on an ordinary PC in a minute or two at most, even for programs of millions and millions of instructions. In both cases, both the scaling law and the Markov chain show that the halting probability is approaching 0 as the length grows. This does not mean that Turing-complete GP is not possible. In fact, as we've shown, it's with simple changes to the parameters of the system, it's possible to get a very good proportion of programs that halt, and so we can get evolution going, even with the simplest possible fitness function for non-halting programs. So this leads us to the end of our talk. I would like to thank you for your attention and for putting up with the technical problems of this talk. Thank you.